All right, good morning, everybody. Let's get started today with chapter 3, or I should say the continuation of. We got into it a little bit, so today I want to go over the table where we left off. We left off with the 7 crystal shapes or crystal systems. And this is basically all the unique shapes that you can fit atoms into, or you can start building a unit cell with. Okay, so here half of the table is listed where you have cubic, tetragonal, orthorhombic, and the parameters that you see on this slide are the lattice parameters. And the lattice parameters consist of the unit cell length. So if they're all the same, some of the systems that we've been talking about are cubic base system. So their lattice parameters A, B, and C are the same. So that's why you see here it being listed as A, because A is equal to B is equal to C, and thus you just need to know one unit cell length, okay, if it's a cubic system. And the alpha, beta, gamma, those are the angles in between your unit vectors, are 90 degrees. That's the definition of a cubic system. Then you can expand upon that and say, okay, well, if A and B are the same, so now you have AA in the plane, but C is different, but all the angles are still 90 degrees, then that's tetragonal. And then you build upon that. What happens when A is not equal to B, is not equal to C, but all the angles are still 90 degrees? Then that's orthorhombic. So that's how we start taking away symmetry, okay? And so these are all the shapes. They're also known as crystal systems. Then we get to more particular and less symmetric crystal systems. So you see here the remaining 4. Rhombohedral. So now A, B, and C are the same, very much like the cubic systems, but the angles in between the vectors are not 90 degrees, okay? And the angles are not 90 degrees, but they are equal to each other. So if all your angles, alpha, beta, gamma, are not 90 degrees, but they're equal to each other, that's a rhombohedral classification. And then you have a particular one, hexagonal. So now A is equal to B, and this was brought up in the discussion forum. How do you describe a unit cell for hexagonal? And so here, I just want to switch over very quickly just to show the difference. Okay. But I wanted to clarify why the hexagonal unit cell looks like the way it does. And I will upload this. I've uploaded a screenshot, but I'll also upload the PowerPoint. I just have really one slide that clarifies this a little bit more. So in your book, it has that hexagonal primitive unit cell on the right. So all I did was just, I mirrored it, which is why why the letters are backwards. But I intentionally did that just to show you, where you could get the primitive unit cell for hexagonal and where the angles are located, okay? So you just have to tessellate that, as you can see, until you get 360 degrees, and now it looks like a hexagon that one would expect in a hexagonal crystal system. Okay. Okay, then you have a monoclinic, and then the least symmetric of all the shapes, triclinic. A is not equal to B, is not equal to C, and none of your angles are the same. And there are quite a number of systems in which this is just how it is. It's not very symmetric, but we have a way of describing the symmetry nonetheless. Or rather, the unit cell that gets repeated nonetheless, okay? And then on top of that, you can build what's called the 14 crystal systems, or the 14 Bravais lattices, because you can have a cubic shape, but where you put your atoms within that cubic shape differentiates one cubic system from another cubic system. So you may have heard of simple cubic, body-centered cubic, face-centered cubic. These are pretty common systems. And so you may have heard it in your introductory physics or chemistry course. But you may not have heard of simple tetragonal, where if you put atoms at these lattice sites right at the corner, and A is equal to B, but not equal to C, and all the angles are 90 degrees, that's a simple tetragonal Bravais system, okay? Now, if you do that, and then you put also an additional atom in the center of this unit cell, now we call that body-centered tetragonal. And there's a specific application in iron when you're dealing with the processing of irons that you will get this BCT type crystal structure. That's not necessarily something that you want. Okay, so it does have real life applications, understanding the crystal structure and how that affects the properties that you measure. And then there are more, right? There's simple orthorhombic, there's body-centered orthorhombic. You could see they're all basically permutations of what the lattice parameters are, so the lattice distance and the lattice angles, and also where you place the atoms, whether they're just at the corners, simple, or there's an additional atom in the center, so that's body-centered, or you have atoms additionally at the faces of the unit cells, okay? So that's face-centered, and then you could see they're all similar, except for hexagonal. Hexagonal doesn't have such a thing. So that's it. 14 Bravais systems built on the 7 crystal shapes. Yes?
For face centers, does it have to be like that front and back of that, or could it be the 2 side faces as well, and it would still be technically face centered?
Yes. So now, so the question is, do all the faces need to have an atom at the face? Yes, by symmetry. Otherwise, once you start putting down an atom and you have some missing atoms, we'll talk about nuanced exceptions such as point defects. Certainly in real life materials, you can start with, say, nickel FCC, copper FCC, aluminum, these are common materials. You can start off with that, but in real life, there's always a point defect, right? You could very well and will definitely have missing point defects, where you're missing an atom there, so you could have a vacancy. But overall, in these systems, you would still say it's FCC and identify a point defect. But you still have that FCC symmetry, all right, face-centered cubic symmetry. And I should say all of these lattice sites are identical, okay? So if you put an atom down here, let's say, and I say, okay, it's body-centered cubic, I've just told you the entire symmetry of the system. That means if you understand the formalism, you know to translate the atoms this way, and 1, 1 over, and you also should know to put 1 at half, half, half of that unit cell. So that's based on the symmetry, okay? So it's not like I have to tell you put an atom here and then put an atom here for body-centered. I should only have to tell you the position of one atom, because then it propagates through translation vectors, okay? Okay. So with that, we'll go into examples of materials with these crystal systems or with these Bravais lattices. There aren't too many examples of simple cubic systems because the world is complex, but there does exist a few. One of them is polonium. It's a great radioactive material for radioisotope thermal generators if you want to send a satellite into space and you need energy for long periods of time. Polonium is radioactive. It will just give off heat, right? And so you could actually use that heat and convert it to electricity using an RTG. And if you're shipping it to Saturn and beyond, whatever distance we're trying to achieve, this is a very good material for that, and it's simple cubic. If you look at the coordination number, so you could see it here in this diagram, but you could also open the crystallographic information file or a CIF that's been formatted in Vesta, and you can just turn it around and see that the coordination number is 6. That's how many nearest neighbors it has. And then if you look at the length of the unit cell, it's just 2 times the radius of that atom. So if you see here, here's one R, okay, and then here's the other R. So the lattice distance, the unit cell length is just 2R. And because it's cubic, it's obviously identical in all 3 vectors, all 3 directions. And then if you look at, okay, well, how many atoms are in this unit cell? It's just 1 atom, okay? Because you have 8 corners, but each of the corner only has 1/8 of an atom. So 8 times 1/8, total of 1 atom in a unit cell, okay? You could also think about it symmetrically. So if you put an atom here, and you propagate using translation vectors and with simple cubic symmetry, well, this atom is actually identical to, let me choose a different color. This atom is actually identical to, excuse me, it wants to advance. Maybe it doesn't like blue. Okay, hold on. I think I just have to switch it back. Okay, let's see if it likes that. So then you translate it to this atom. And then if you think about it, this atom is actually just this atom. So this is 0, 0, 0, if you consider that as the origin. Well, now this is the new 0, 0, 0 for this second unit cell. Okay? So you really only have 1 atom by symmetry. So you could think of it 2 ways. 1, how many atoms do I have to put down, and then it just gets propagated through translation. Or 2, you take a look at the unit cell here, and you say, okay, how many atoms, how many fractions of an atom are actually in that cell? Either way, you get the same answer. Yes, all the way in the back.
Does coordination number refer to the number of unit cells, neighbors, or the number of atoms?
It refers to the number of nearest neighbors. How many atoms is it coordinated to? Okay, so let me explain that. Let me give a better example. Okay, the same can be done for body center cubic, BCC, typical elements, vanadium, chromium, alpha, iron, molybdenum, tungsten. And of course, you can look this up in the periodic table as well. The coordination number is 8. That means there are 8 nearest neighbors. So you could do that if you're at, you can just do that count. If you're at this atom here, you can count 1, 2, 3, 4, 5, 6, 7, 8. Yes?
I see how it works with that, but what about the ones like on the edges? That does not look like 8 neighbors.
Edges. You mean at the corners? Okay. Yeah, I only specify that. So what happens at the edges was the question. There aren't edges per se because these atoms are at the corner. Okay, so there you could see it's only 1/8 of an atom, if this is how we define the unit cell. And there are 8 corners, 1, 2, 3, 4, 5, 6, 7, 8, and thus there are 8 of an eighth of an atom, and thus you have 1 atom. And then there's one big atom in the center that you see here, and thus there are 2 atoms per unit cell when you consider the fraction of an atom at the corners, 1/8 of an atom.
Consider the one like that's in the center position as an actual atom. All the ones on the corners are
Fractional. Yes, yes. So you could see, so this is also, this figure is from your book, and it does a good job of showing the lattice points, okay, where you have half, half, half here, and then you have 0, 0, 0, but that's translated. So you have the atoms at the corner, okay? And then here it does a good job showing the fractions of an atom that's at the corner, and then this is just all the atoms propagated. It's not a very useful rendering because they're all just like gray balls next to each other. But I think these two are much more helpful to help you visualize. And once again, you can dig up the BCC crystallographic information file and do the same thing to answer your question. And then the length of a unit cell as it relates to the atomic radius is given in this ratio, this relationship here, where the ratio is 4r over root 3. Okay, and we'll go over how one arrives at that. Then the next example is FCC. So I've listed some common examples, copper, nickel, aluminum. You also have gold, that's FCC, and platinum, one of the most expensive elements and also material. Coordination number is 12, and the length of the unit cell as it relates to the atomic radius is 4r over root 2, and the number of atoms in the unit cell is 4. So now this goes back to your question, what about the edges? Here, it's not really an edge per se, but we're talking about the face. So half of an atom is at each face, and you have 6 faces. And at the corner, once again, it's 1/8 of an atom. So 8 corners times 1/8 of an atom is 1. So 3 plus 1 is 4 atoms, okay? That's how we count atoms per unit cell. Yes?
Will we be required to memorize those 3 equations?
Yes. The question is, are we required to memorize that? Yes. These are some basic fundamental properties of these crystal systems, so most definitely.
Just memorize what you just told us?
Yes, but also understand where they come from, right? Do the counting, practice the counting, okay? Because in reality, you can memorize this, but there are 230 space groups. We're just going over 14 Bravais systems, so you should understand how one gets at these numbers, which is why I'm going into great detail how I count them, okay? But these are the common ones. So if you commit this to memory, it's very useful for these, okay? And then hexagonal Closepacked. There's a reason why it's called Closepacked, and we'll talk about atomic packing fraction and why hexagonal Closepacked, or HTP, and FCC, or cubic Closepacked, have the highest packing fraction. Some typical elements are beryllium, magnesium, alpha titanium, very important, zinc. Coordination number also 12. The length of the unit cell here is A and C. C, there's a relationship between C and A, and that's derived in your book, and I won't do that here. And the number of atoms per unit cell, if you do this calculation, you should see that it comes out to 2 atoms per unit cell, or you have fractions of an atom at the corners, at the intersection of two vectors, but they're not the same. So this one is 1/6 of an atom. This one is 1/12 of an atom. And there's 1 atom in the center. So let me show you that. not coming up. Interesting. I don't know what to say. Okay. All right, we'll give the last person a few seconds, number 169. Okay, so it's 4, let's see. Fabulous, we've all been engaged today. This is great. So either you looked back at your slides 2 slides ago, which is great, thank you for reading, or you paid attention in class. Either way, fabulous engagement. Okay, and those of you that had some glitches, please email Natalie. I don't think we need to belabor the point and go over this. Okay. Oh, pardon. Okay, voila. It is definitely 4. Okay, so we'll go over this. I will not present it as a top hat. We'll just do this all together. So we discussed before how to relate the lattice parameter or the lattice length A in a cubic system, particularly FCC, to the radius of the atom. And so there you just need to look at, and for all these systems, you just need to see where the lattice, where the radii of the atoms touch each other, where you have a continuous length and there aren't any gaps. So for FCC, there's a particular way of doing that. You look at the face, right? So if you look at one edge, let me choose blue, hopefully it's still blue. Yeah, so if you look at one edge, you could see that there's a bit of a gap. So you can't really relate the lattice parameter to the atomic radius. But if you look at the lattice, the face diagonal, you could see that there are 4 atomic radii all connected, right? So here's 1r, here's 2r, and here's another r, okay? And so there you can relate via Pythagorean theorem what the lattice parameter should be in relation to r, okay? So if you do that, you see, okay, well, I have the triangle a squared plus a squared equals my face diagonal squared, or a squared plus b squared equals c squared, okay? And then you say, okay, well, that's 2a equals my face diagonal squared. And so the square root of that is square root of 2a, right? That's how that relationship is. But the face diagonal, we just said, is also 4 atomic radius length. So if square root of 2a is equal to 4r, you get this relationship, okay? You get a is equal to 4r over root 2. So should you remember this? Absolutely. Should you also know how to derive this? Also absolutely, okay? But that's how one goes through the process of relating lattice parameter to atomic radius. Yes?
Are you capable of doing this with all kinds, or is it just with the FCC?
There are several that are simple, and those are the systems that you'll be asked to know, which is also in your book. For very complex systems, absolutely not. I mean, that's really unfeasible. That's not realistic. And, you know, so. But the highly symmetric systems, absolutely. So whatever's in chapter 3, yes. Okay. BCC, once again, we'll go over this as a group. So BCC lattice parameter, right? how do you relate the lattice parameter to the atomic radius? You do the same thing, except at the face, if you recall the diagram, there isn't just a continuous, it's hard to see here, but if I draw the face diagonal, there's a gap in there, right? Because now there's an atom in the center. So there you have to cut through the body diagonal to get the relationship between the lattice parameter and the atomic radius. So how does one do that? Well, you look at, this is a better visual. So if you cut through the body diagonal, you also cut through 1R, 2R, and another R. Now this visual is a little bit difficult. I shrunk the atom, so it's hard to see that it's actually 4R, but it is. I shrunk just so it's a little bit more clear. But your body diagonal is 4R. Now what's the relationship between that versus the lattice parameter? Well, here you have the lattice parameter given as some A, some value, right? And then that triangle with the body diagonal is made up of this side and the face diagonal. But as we know from face-centered cubic, this relationship, if you have A here and A here, the face diagonal is just square root of 2A, okay? And so now if you have one side is square root of 2A, the other side of the triangle is A, you have the body diagonal length as square root of 3A. Just Pythagorean theorem. So then you relate A to the 4R that you have. So if you have 4A, if you have your body diagonal is square root of 3A, but that's 4R, that's the relationship that you have. You just divide it by 4R, okay? And that's it. So same procedure, same methodology as FCC as it is for BCC. You just have to find where the atoms touch side by side, and that's how you get the distance in atomic radius, okay? And also, this is for a BCC system where all the atoms are the same, okay? We have not touched upon ionic systems where you have a cation and you have an anion, and each of those have ionic radii that are not the same as each other, okay? Questions? Okay. Right, so I've gone over these specific examples, and I've summarized them here why we should care about these particular examples. All right, so you have BCC, FCC, HCP. These are relevant crystal systems for broad-based systems for the elements that you interact with every day. Right? So those are highlighted in the different colors that you see here. So in blue, pink, and green. So you can just take a look. Obviously, you don't have to commit everything to memory, but you definitely should know when given a Brave system how you should treat it, how you count coordination numbers, and how you can relate the lattice parameter to the atomic radius. Okay, so now packing fraction. We're going to start talking about density. How do we think about how atoms pack? There are consequences to how atoms pack and their mechanical properties. If something is more dense than another material, right, we have to think about that in terms of, do we want to use this material and incorporate it in applications when we're trying to lightweight something or use it in structural steel, you know. So these are the things we talk about. And one of the things we talk about is atomic packing factor. So that's just by definition the volume of your atoms in your unit cell divided by the volume of that unit cell. So it's been brought up in some of the questions where, you know, the atoms that are in the unit cell, they don't take up the entire unit cell volumetrically, right? You see gaps in there. So that's what we're talking about when we talk about the atomic packing fraction, is how much of that unit cell is taken up by the volume of the atoms themselves. And the way you would calculate that is you need to know the number of atoms per that unit cell, right? So it's 2 or 4 or 1, depending on the crystal system. And then, of course, you need to know the volume per each atom. So you know that there are 4 atoms in FCC. Well, it's different. The volume of each atom is different for different types of atoms, right? It's different for iron versus nickel versus platinum versus palladium versus silver versus gold. I mean, the list goes on, right? And then you need to know that's normalized by the volume of the unit cell itself. So you see some of the cubic systems, well, the volume of a cube is just a cube. It is just that simple. Okay. So here's an example of the atomic packing factor for BCC. We know that there are 2 atoms per unit cell based on our counting system, right? Based on the way we've counted the fractions within this unit cell that you see here. And then you know the volume of each atom, because if we treat it as a hard sphere model, it's just a sphere, so it's just 4/3 pi r cubed, right? And the atomic radius, these are all in a database, so we know these values, we've measured these values. And then the volume of that unit cell, as I've just mentioned, it's just a cube, okay? So here, if you go through the math and normalize everything and cancel out all the numbers and all the values, you get a fraction of 0.68. That is the packing factor of a BCC system. That means 68% of your unit cell comprises of your atomic volume. Okay. And the magic in this step is knowing this relationship. Right? We knew from BCC, from our calculation before, that it was just this. So I just inverted R, okay, and then inserted into that relationship. Okay. And then you start canceling, and you get this. And you compute all the numbers. That's it. So that's the atomic packing factor for BCC. And then similarly for FCC, one goes through the same methodology. Atoms per unit cell times the volume of each atom divided by the volume of the unit cell. Yes?
I see where the equation is coming from. Where do those numbers get added from? Just from like random numbers you're plugging into the equation?
I'm sorry, what numbers? Which numbers are random?
Never mind.
Okay, well, okay. So hopefully that's clear where all these values are coming from, right? They're just by definition volume, the volume of an atom, of a sphere, and a volume of a cube, okay? Same thing for FCC. Number of atoms in a unit cell, 4. Volume of an atom, 4/3 pi r cubed. Volume of the unit cell, it's cubic, a cube. So once again, you need to convert the R to A so that the lattice parameters cancel out, and you get a fraction of 0.74 or 74%. That's how much volume of your unit cell is taken up by the atom. So clearly, it's more dense in a FCC system than it is in a BCC system. Okay? Okay, well, I've just given you that answer. The density of BCC versus FCC is smaller because I just said FCC is more dense, okay? That's the logic behind that. Okay, we will also skip that, but I will leave that for practice. Okay, when we talk about close-packed structures, there are 2 that are particular, and they're based on symmetry and how we stack the atoms. So here's a figure from your book where it shows the difference between HCP and FCC. So FCC and HCP had the same packing fraction, 0.74, but if you think about how you can pack the atoms, the only difference is how you stack the sequence. So for FCC, you could see that the close packed planes, so these are the planes in blue here, where all the atoms are touching each other, okay? And so if you look at the close pack, you see all the A atoms. So in one layer, that's labeled A. The next layer is labeled the B atoms, and then the next layer after that, the third layer, is labeled C. So basically, you can have atoms, and the next layer, you can put them at an interstitial. So if you have 3 atoms on the first layer, there's a hole in the middle, right? So the next layer, the second layer, you can put an atom right there and propagate the same type of symmetry. So that's for HCP, and you do A, B, C, A, B, C. You can stack it in that way. For HCP, the sequence is just A, B, A, B. So if you compare the 2 lattice, the close packed planes, they're quite similar. It's just the sequence is off. So you could go A, B, And then you could choose C, or you could go back to A. And that is the difference between the way atoms are stacked in the Closepacked planes, okay? I just wanted to note that that's a subtle difference. Okay, so all this talk of crystal structure and atomic packing, you could see that there are trends. So metals tend to have these structures, FCC, HCP, so they're close packed. And you could see this whole range here, and you could see how it affects the density. Then when you move to ceramics, polymers, and even composite systems, you could see that the densities change quite a bit for ceramic type materials. Polymers are less dense because now you have the secondary type bonding. You also have amorphous regions where it's not perfectly crystalline. So the crystal structures that we've talked about, right, that's based on the assumptions that all the atoms are at the lattice sites and they're closed packed for FCC and HCP, or they're crystalline in some way. There's an example of what happens if you have a defect. Well, what happens if you have a lot of defects, right? What happens if you don't have crystalline periodicity? Well, you have lower density. Okay. Yes.
Are there some notable exceptions that we need to know, or
such as?
I don't know, some ceramics that can be more dense than metals or something like that? I don't know. Any notable exceptions we need to know?
Potentially, if the two ratios of the cation and anion, right, are close to each other, then you're basically approaching a system where all the atomic radii are the same. You don't have to memorize any notable exceptions. Okay. But you should know the trends between metals, ceramics, polymers. Okay, so theoretical density. Very simple. As you recall, density is just mass over volume, right? And so the way we relate that in terms of the number of atoms in a system or in the number of atoms in a unit cell is just defined here, where your density is the mass of atoms in a unit cell divided by the total volume of that unit cell. Once again, the total volume is just defined by your unit cell and the geometry of your unit cell. So here, we can just relate it as the number of atoms in the unit cell n times its atomic weight in grams per mole. And the total volume of your unit cell is just that times the number of, times Avogadro's number, right? Because that's how many unit cells you have in your system, in your particular material. So the only things you need to know are the number of atoms in your unit cell based on symmetry. And then, of course, how do you calculate the volume of that unit cell? The atomic weight is given, in a database in the periodic table. So obviously, that would be tabulated. You wouldn't have to memorize that. And Avogadro's number is just Avogadro's number. Okay, so that stays the same. So it does relate back to knowing how many atoms are in a unit cell, given if it's simple cubic, BCC, FCC, HCP. Okay. Okay, so in the interest of time, I will post this answer for you to practice, but it goes through the rigorous exercise of how to calculate the theoretical density of copper, right? So if you plug in the values here that I've just gone over for copper, you can see copper is FCC, so there's 4 atoms per unit cell. And its atomic mass is 63.55 grams per mole, and that's given in the periodic table. And well, cubic volume is just A cubed, and Avogadro's number is listed here, okay? So once again, you need to know the relationship between atomic radius and the lattice parameter. And so, as you recall, we worked out how to get to this relationship between A and R. So if you plug that in, you can look up, or you'll be given the atomic radius for that particular element. Here it's copper. And you crunch out the numbers, and it's within the range that one would expect. So 8.89 more specifically So you should also know, what are the reasonable ranges for a metal. 50 is pretty high and unreasonable. 0.1 is very low and unreasonable. 8, 9, these are reasonable numbers for density of a metal that is FCC, okay? So that's how you can also check yourself. Does this number make sense? Did I punch something in wrong into the calculator? Before you even start discussing it, you can just look at the number and look at look at your range. Did I get something wrong? That's in engineering. That's basically the easiest way to catch an error. Is am I even within a physical limit of these numbers? Okay. Okay. So now we will get to ionic ceramic crystal systems. I want to go back to this example of coordination number and ionic radii to discuss how these systems are arranged and how they're different from metallic systems. And I believe there was a question about sodium chloride being cubic and whether or not cesium chloride is also cubic. The answer is yes. But if you see here, it's not exactly body-centered, okay, for cesium chloride. If you look at it, you have definitely one atom at the center, half, 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 in terms of fractional coordinates. And you definitely have atoms at the corner, and this definitely resembles the symmetry of BCC. But it is not, because if you look at the individual symmetry of the cation versus the anion, it's quite different. So let me show you the difference. Okay, let's switch back. Okay, so I went over this example for ionic ceramic structures. This is just written out what I've just said. And if you're having to calculate the anion to the cation to anion ratio and looking at coordination numbers, you could see that this ratio would give you actually a coordination number in this range for 6. Okay, and you can count that. You can go back into the example and see that if you sit at this, iron oxide or nickel oxide or sodium chloride system, you can count the number of neighbors. So here's the cation. So you have 1, 2, 3, 4, 5, 6 anion neighbors. Okay. It's easier if you just sit down and play around with Vesta and visualize this. Okay. Now, there's a homework problem in homework 1 where it deals with this calcium fluoride or calcium difluoride structure. And what I want to say about this system and relating A to the atomic radius is that you want to see which direction, once again, where the atoms are touching. In this case, where the ions are touching. So here, you want to focus on the cation connecting to the anion here. So you know that there's one R here and one R here, but this R is for the cation and this R is for the anion. And you want to find out what that relationship is. Okay? So build your triangle the same way, going through the body diagonal, and calculate that relationship. So use the same Pythagorean theorem technique to relate A to R. Okay? Okay. I am trying to keep us on track. So I will go through to ionic packing factor of calcium oxide, which also has sodium chloride structure. So similarly to atomic packing factors for ceramic systems where you have ionic, we call it the ionic packing factor. And as I've said, the ionic radii are different for the calcium 2+ versus the oxygen 2-. And so if you look at how do you relate the lattice parameter to that of the ionic radii, you could see that here along this edge, there's 1R for the, well, I coded it in red, so it will be minus, and 1R here for the anion, and then 2R here for the cation. And so if you calculate the volume of the unit cell and also the volume of the atoms, you can get the ionic packing factor based on the 2 different ionic radii. Okay? Same methodology. Now you have 2 different values for radii. Yes? Is the first line supposed to be 0.0106? That is correct. Thank you for catching that typo. Wait, 0.106, 132. This value is definitely correct. So it should be actually it should be 0.1. Is that true? Yeah, so here's my typo, I think. Sorry. Thanks for catching the typo. Okay, so questions on atomic packing factor, ionic packing factor, how to relate A to R for metallic systems versus ceramic systems, and also 7 crystal systems versus 14 Brave systems. Okay, with that, we will adjourn for today and pick up next time on chapter 3, okay?